At least three elements are essential to be addressed by the design for top and bottom captured glass systems. Design should promote an efficient installation. They should be thought out in such a way that the materials can be installed as intended without an undue burden on the installation team. Design should be feasible. This means that they should have parts that are compatible with each other. For example, you would not use a bottom rail that supports a half-inch thick glass and a top rail that supports 3/4 inch thick glass. The design also needs to meet applicable building codes, specifically the loads that are imposed on the glass wall. The deflection needs to be limited so that you don't have the separation between panels. And we need to have adequate structural anchorage. They also need to be feasible by allowing for tolerance appropriately. Anticipating tolerances in the correct amounts is by far the most challenging aspect of designing top and bottom captured glass systems. Ideally, our designs will be able to realize a successful result in at least 95% of cases. The elements of a top and bottom captured glass system include frame receptors, perimeter fasteners, glass, the joints between the glass, and door systems. The most popular type of receptor element is a U-channel. U-channels are a relatively inexpensive means of supporting the glass along its top and bottom edges. Receptor elements do not have to be the same size at the top and bottom. They don't have to be the same shape at the top and bottom either. Ordinarily, they will both be the same finish, but that's not necessarily required. It could be specified differently. We most commonly use a 1-inch U-channel. We frequently use an 1.5 inch or a 2-inch U-channel. Normally, the deeper U-channel will be used at the top. When the glass is installed, it's lifted up on a tilted angle so that the edge of the glass goes into the top, and then it's swung so that the glass is vertically plumb, and then it's set down into the bottom channel. The top being deeper, the glass is retained in both the top and the bottom channels in its finished state. CRL offers this vinyl to be used in conjunction with the 1-inch U channels. They have a different thickness gasket for 3/8 and 1/2 inch glass to go with those U channels. And this rubber material takes up the space between the glass and the channel. Remember, we don't know the actual thickness of the glass. There's a tolerance for that. It's about a 32nd of an inch for 1/2 inch glass. And we also don't know the dimensions of the channel. We have about a 1 degree allowance for the angle at the side. So we use a rubber gasket to take up and fill the space between the glass and the channel. CRL also offers what they call architectural U-channels. If you're looking at a product offering in terms of good, better, best, this would be a better option. These profiles are provided in anodized finishes, and they're also provided with stainless steel cladding and other metal finish types clad over the aluminum channels. They're available in what they call a shallow profile, which is 13/16 tall, and 1 5/8 tall. The shallow channel is not used at the top and the bottom because it doesn't allow a sufficient amount of glass bite. Finally, CRL offers what they have termed base rails. These are available in a variety of heights and shapes where they have a tapered and a square version. These have a variety of end caps as well, different types of rubber gasket. They're available to support 1/2 inch and 3/4 inch glass thicknesses. Moving on, it's important to take a look at fasteners and how they transfer force from the glass to the structure. Taking a look at a cross section of the top channel, we see a force being applied to the glass, that force being transferred into the channel. The first thing that happens is the glass begins to bend, it deflects. As the glass deflects, it gets pulled out of the top channel. If you install glass and the rubber falls out of the top, it could be a result of deflection. And depending on how much glass bite you have at the top, perhaps an insufficient glass bite and excessive deflection, and you end up with loose gaskets. The force of the glass pushing against the channel causes the channel to begin to bend, and this bending and force of the channel applies a pull-out force to the Tapcon. It's much like a hammer pulling on a nail. In order to understand that force a little better, we'll take a look at the geometry here. We have a 2-inch channel that's 1 inch wide. That means our channel has leverage over the screw. 2 inches divided by a 1/2 inch gives us a factor of 4. So the amount of force that's applied to the glass transfers to the channel, which acts as a lever like a hammer pulling out a nail. 4 times the applied force is transferred to the screw. The screw experiences a force which pulls it out of the structure that it's attached to. If you recall, the building code requires the glass to resist 50 pounds a linear foot. That's section 2403. 50 pounds times 4 is 200 pounds. So there's going to be 200 pounds of pull-out force applying to each linear foot of the channel. Fastened connections can fail in a couple of different ways. There's a pull-over failure. That's when the material being fastened just pulls right off of the screw. Screw stays in place, it's still in the structure, screw didn't break, but the material itself has a bigger hole in it because it ripped off of the screw. We're talking about pull-out performance, which is shown in the illustration to the right. It's where the screw itself rips out of what it's screwed into. There can also be screw failures where the tension exceeds the strength of the screw and it just snaps in half because it's pulled apart. There can also be torsion strength failure where the screw is over torqued and the head snaps off. It's relatively common. And finally, screw fasteners can fail when their shear strength gives out. That's the slicing, cutting type of force that cuts the screw in half. Just for reference, a 1/4 inch diameter Tapcon, 1 inch edge distance, 1 inch embedment into 2730 psi concrete has a pull-out strength of 668 pounds. Similar tables are available for self-drilling screws. As with Tapcons and all other fasteners, pull-out strength depends on the strength of the material that you're attaching the screw to. What's noteworthy with the self-drilling type screws, the pull-out strength is very closely related to the drill point that's used to make the hole. Wingtech screws are used to cut wood out so that when you attach wood to metal, the wood stays against the metal. The wings on the screw effectively remove the wood so that the screw threads don't pull the wood away from the metal. Those wing tips are designed to break off when they go through steel, but we should not be using those type of screws to create holes where we're attaching channels to metal at the top. Those wings can cause the hole to form in a way that is not as tight and we don't have as strong a connection. When we don't have a strong connection, our channel doesn't sit quite as tightly, and when the screw experiences pull-out force, deformity takes place, vinyl gets loose. And we see in this table, they have a couple of different 1/4 inch diameter screws. We primarily use a 1/4 inch with 20 threads per inch. We're only ever going to use 1/4 inch screws. Now the information that we have relates to a number 3 drill point. Just for reference, the self-drilling screws, they all have a similar shape drill point, but there are sizes 1 through 5. Size 1 being the smallest, that's for drilling holes in very thin material. Size 5 has the longest flutes, and size 5 is for drilling holes in a thicker material. The other essential part of this table is the metal stud gauge. That's the thickness of the metal stud. Metal studs come in a variety of sizes and thicknesses. Typically, 20 gauge metal framing is used at the interior for non-load bearing walls in commercial buildings. For our purposes at Door and Glass, we're going to be using the self-drilling number 3 tip flathead countersunk, similar to the pictured screw. It's not going to be a Tapcon at the top of the frames attaching to metal. Achieving the pull-out strength listed in the table critically requires that the hole which is drilled for the fastener be tight to the threads on the screw. And of course, the pull-out strength changes entirely once you remove the screw and put the screw back in the same hole. This diagram shows the ideal way that self-drilling screws become attached to a metal structure. You can see that the screw ideally reforms the metal material that it's attaching to maximize the thread engagement in that material. That's going to provide the most beneficial pull-out strength value. As an example, we know 50 pounds per foot times a leverage factor of 4 gives us a 200 pound per foot requirement. That's from the building code. 1/4 20 screws, number 3 drill point into a 20 gauge stud. That gives us 337 pounds per screw pull out strength. 337 divided by 200 pounds a foot, it gives us 1.685 screws per foot required to support the load. Of course, we can't provide 1.6 screws, but we could space them out a little bit more. 1.685 times 12 inches per foot gives us 20.22 inches. So we could install screws at 20.22 inches on center, but it's easier to attach screws at the top and at the bottom, and you never want to have a safety factor equal to 1. You always want to have a safety factor greater than 1. So if we go with screws 24 inches on center at the top and at the bottom, we're going to achieve a safety factor. We spoke previously extensively in the code section about glass and glass requirements. We want to make sure that we limit deflection and attach the panels to each other so that they can't move independently. Moving on from there, there are a limited number and type of joints and joint conditions that can be created in top and bottom captured glass systems. The variety of different ways that joints can be configured is limited to a relatively small set of possibilities. It's important to recognize that there are 2 different vertical joint conditions. One occurs at intermediate vertical joints, those are the joints between the glass panels, and the other occurs at the perimeter of these openings where the joint occurs between a glass panel and the structure. So we have intermediate and perimeter conditions. And next we have a limited number of different possible orientations. That's the arrangement of the panels relative to each other. Most often, the panels are going to be in line, forming a straight line with each other. That'll be an inline joint, 180-degree orientation. And the alternative is there's an angle. The panels form an angle that's not 180 degrees, so they're not lined up in the same straight line. The different types of joints which are available to address these conditions and orientations are mostly the same. The vertical intermediate joints between adjacent glass panels which are in line with each other can be created in 5 basic ways. Commonly associated type of joint is a silicone joint, where a relatively transparent silicone material is applied between the glass panels. We'll provide a detailed explanation of how to construct this type of a joint between adjacent panels. The typical joint size for this is going to be 1/4 inch. That's what we would deduct when we're converting our opening measurements into glass sizes. We're going to allow 1/4 inch for the size of a silicone joint. Size between the glass panels can vary by 1/8 of an inch per the uncertainty in the cut size of the glass material. Next, we have a joint where no material is provided. We only have air between the adjacent panels, and they're not connected to each other. This type of joint is relatively common, although we understand that it does not allow us to meet the building codes unless we use a thick enough glass to limit the deflection. Deductions for this size joint are going to be 3/16 of an inch. It's very important that the glass panels cannot touch each other. Their edges can't touch, or they're going to create chips. The panels will damage one another because eventually they are going to be experiencing loads and causing some deflection. If the panels are touching, they're going to end up creating chips in each other. So we want to deduct 3/16 when we're converting our measurements into glass sizes, and the joint size is going to be plus or minus 1/8 of an inch. So it could be 1/16 to 5/16 of an inch. Next, we have really similar to an air joint, we have a mechanical clamp that's used to attach panels to one another. There are a variety of different types of clamps, and these clamps are in different metal finishes. Some have fasteners, some rely on adhesives. We also have an option to use copolymer strips. These are a transparent plastic material that has adhesive tape on it. The important thing about this type of joint material, it's a specific thickness, 0.82 inches. And it's important that our glass deductions are for the thickness or the size of this material that goes inside of the joint. There should be no space in between here. This is a difficult type of joint to create because we have 1/8 of an inch of uncertainty in the glass size. When we create joints of an exact dimension, it's very important that the system's design includes some element to take up the additional space that will result from errors in the glass size. Usually, we're only going to use this type of joint material when we also have a receptor at the vertical perimeter, which can accept more or less glass to take up the error in the cut size. CRL also offers a pre-extruded silicone gasket that can be used at the glass-to-glass joints. CRL recommends that 1/4 inch be allowed between adjacent panels. In our experience, we found that the gasket will stay in place if the dimension between panels varies from 1/4 inch, but only slightly. If it's wider than a 1/4 inch, then we end up with a condition where the gasket is loose and can fall out. And if it's much tighter than a 1/4 inch, it can be difficult to install. As with the copolymer strips, the use of this type of material in a joint requires an exact dimension, or at least a dimension that is much more precise than glass fabrication can afford given the tolerance on the glass size. And so, whenever we use this type of a gasket, we have to have some means of accommodating the tolerance in the glass size. Usually this tolerance can be accounted for by providing a vertical receptor element at the jamb location. Vertical intermediate joints, which are angled where the adjacent glass panels meet at an angle other than 180 degrees, so they're not in a straight line. These joints are almost all the same as with panels when they meet in a straight line. We can still have open joints where there's only air between them. They could be mechanically bound to each other. Copolymer inserts are available for 90-degree joints. The extruded silicone gasket is not available to be used at 90-degree joints. Hand-applied silicone can be used. There's one option which is available to be used when panels meet each other at an angle that's not available when they don't meet at an angle. And this option has to do with the angle on the edges of the pieces of glass. The edges of the glass can be mitered along their length so that the panels meet each other with mitered edges. But the panels don't have to be mitered. They could also have square edges, and most of our customers expect that the panels are going to have square edges. They're not aware that the panels could have mitered edges. Mitered edges are created on glass panels by machines called edge polishers. Edge polishers use a series of steel wheels that have diamonds impregnated on them to grind the edges of the glass and then polish the edge. These machines can be adjusted to create a straight flat edge or an angle. Some machines are adjustable to any angle setting. Some machines can only be adjusted to produce 22.5 degree or 45 degree miters, which is why not every glass fabricator will produce mitered edges in any custom angle. Some of them only produce the angles at 22.5 or 45. Sometimes the hardware for other than a 90 or 135 degree corner is difficult to find because other than those two angles, they're not standard. Most commonly, we're going to create corner joints with glass panels that have square, not mitered edges. There are two ways that we can create this joint. It almost might seem like the same thing, but which panel overlaps the other is an important consideration. We would like to create the most aesthetically pleasing result, and that means we don't want to have too many lines in the glass. Now, when you're viewing the glass straight on, it's going to be reflecting light, and if the panel at the end of the elevation stops short and you see the other panel, that reflection doesn't carry through in the same way, and it's going to bring more attention to the joint. Using this elevation as an example, the panel on the end, we would want to overlap the adjacent panel. It's going to create a more seamless appearance because we're not going to see an eighth piece of glass in this elevation. Well, not exactly. We're going to be able to see the edge of the returning panel, but our impression from this perspective is going to be less busy because that reflection from the leftmost panel is going to carry through and not be interrupted by a joint and then an adjacent panel's edge. The ordering of these joints is going to depend really on the layout of the building. If, for example, we had a high traffic area here, then the 3 panels might overlap. And if we had a high traffic area over here, then this panel might overlap the adjacent panel. In general, the elevation which has the overlapping panel is going to appear to be a little bit less busy. And so the decisions as to which panels overlap which other panels are generally made by looking at the floor plan, the space itself, how people are going to walk through the space, and you would want to provide the most seamless appearance from the most populated or heavily trafficked areas of the building. Now, as you know, there can only be a finite number of different ways of creating these corner joints. An option is for us to have nothing between the panels, only air. When we elect to use that option, we're going to deduct 3/16 of an inch. We can also use mechanical clamps at the corner condition to fix the panels to each other. The clamps can, like inline joints, they can have a fastener or they can rely on adhesives to hold that joint oriented, to hold the dimensions of that joint fixed. As with the inline joints, you're going to want to consult the specific hardware instructions to see what should be allowed in terms of the dimensions of the joint. And finally, we have the mitered joint condition. The mitered joint condition can never only have air. It could have a mechanical fastener. We're going to allow a 1/4 inch between the glass panels at the corner condition. In order to achieve that joint dimension, we're going to deduct a 1/4 of an inch from the length of that portion of the glass wall, as you can see in the diagram. And finally, we have the copolymer strips for 90-degree corners. Again, this has a very specific 0.82 inch dimension associated with it. So you'll want to have a receptor element or some other means of accommodating variation in the glass size that's cut. You wouldn't use this type of a joint without having the ability to accommodate variance in the glass size. The company has certain standards for its performance of top and bottom captured glass. Top and bottom captured glass systems are installed into openings, ordinarily at the interior of buildings. The openings can have some variation, but if you remove all of the substrate from consideration and just focus on the material itself, what we're doing is we're arranging this material with respect to itself, ignoring the substrate for a minute. We want to look at how this should be constructed. We're interested in creating an aesthetically pleasing result that's structurally sound. In order to do this, we need to comply with codes. Our bottom receptor, it's critical that it's installed level, okay? And it's going to have some screws that may need to be shimmed. When we use shims, because our channel is only 1 inch wide on the bottom, we have to pass a hole through the shim so that it doesn't wiggle and jiggle and fall out. And our screws are going to be a 1/4 inch in diameter, and we need to use an adequate number of fasteners to support a load of 150 pounds per linear foot, which is 3 times the amount of force imposed by Code Section 2403. In order to support that amount of force, we're going to use anchors at 24 inches on center. Now, the amount of force that any specific anchor is capable of supporting is going to vary based on what we're attaching it to. If we're attaching it to a heavy gauge metal stud, it'll support more force than if we attach it to a lighter gauge metal stud. But without really getting into the weeds and trying to optimize the design on every single project, it's a couple of screws, We expect that we're going to be good when we get into an interior space and we anchor these systems at 24 inches on center with 1/4 inch diameter fasteners, which should always be countersunk. Where other receptor elements are used, they should be mounted directly to the substrate. The ends of receptor elements should be within 1/16 of an inch of a butting substrate. Where receptors abut one another, the maximum allowable offset is 1/16 of an inch. Where vertical receptor elements are used, they should abut the horizontal element tightly at the top. Receptor elements do not receive caulking along their length, but they may receive caulking where their ends are cut short. The cut ends of receptors should not be exposed in the finished state. Cover plates matching in finish to the receptor should be applied to the cut ends of receptors where they would otherwise be exposed. The thickness of cover plates should not exceed 40 thousandths of an inch. Vertical edges between glass panels and substrate should be 1/4 inch if not otherwise specified. That is, when we're converting field measurements into glass sizes, we want to allow 1/4 inch of space where the glass meets the substrate at the vertical condition. Vertical edges between glass panels and substrate should be within 1/8 of an inch of parallel as measured at the top and bottom extremities of the joint. That is, the difference between the measurements at the top of the glass and the substrate and the bottom of the glass and the substrate should not be more than 1/8 of an inch. Vertical edges between glass panels should be within 1/16 of an inch of parallel, as measured at the top and bottom extremities of the joint. There should not be edge reflection in the finished result. A minimum 1/4 inch of the glass bite into receptors is required to avoid edge reflection. This is critical at the top receptor, where deflection causes the glass to pull out of the receptor.